a plane lands safely. The software controlling its navigation contains a bug. A bank processes millions of transactions overnight. Some of the math inside is technically wrong. Your phone unlocks instantly, routes you through traffic, streams video in 4K. Under the hood, parts of that code are incorrect, not broken, not crashing, just wrong. And yet, everything works. That's the uncomfortable truth about modern software. Correctness is optional, at least sometimes. There are systems running the global economy right now that engineers know are flawed. They've measured the error, they've documented it, and they've decided to ship anyway, not because they're careless, but because fixing it might make things worse. Code doesn't live in a clean, logical world. It lives in deadlines, hardware limits, floating point math, and human compromise. Tonight, we're not talking about rookie mistakes or sloppy programming. We're talking about code that is provably wrong and still trusted with airplanes, money, medicine, and your daily life. And once you see why this happens, you can't unsee it. To understand how wrong code can still work, you have to unlearn a comforting myth. The myth is that software is logic made real, that computers are precise, that code either works or it doesn't. That myth died quietly decades ago. Early computers were simple: limited memory, limited speed. Programs were short enough for one person to fully understand. If something was wrong, the machine usually made it obvious. It crashed, it froze, it refused to cooperate. Modern software doesn't do that. Today's systems are layered on top of layers on top of layers. Your phone alone runs tens of millions of lines of code written by thousands of people who never spoke to each other, across decades, across companies, across continents. No single human understands the whole thing. And here's where it gets interesting. Computers aren't actually good at math the way we imagine. They don't store numbers the way we write them. They approximate, they round, they cheat. Because real numbers don't fit neatly into binary. Ask a computer to calculate 0.1 plus 0.2, and it doesn't get 0.3. Not exactly. It gets something very close. Close enough to pass most tests. Close enough to ship. This isn't a bug. It's how the system works. Now, scale that tiny error across billions of calculations per second, across financial systems, physics engines, medical imaging, machine learning models. Engineers noticed this early on. In the 1980s and 90s, famous software failures started surfacing: missiles missing targets, rockets exploding because two systems disagreed on a number's size, bank balances drifting by fractions of cents that somehow turned into millions of dollars. The lesson wasn't make code perfect. The lesson was more uncomfortable. Perfect code is often slower, more expensive, more fragile, sometimes impossible. So software teams started making a different promise. Not correctness, but usefulness. Does it converge fast enough? Does it fail gracefully? Does it stay within acceptable error? If the answer is yes, the code ships. This is why software specs are filled with phrases like within tolerance, best effort, and expected behavior. Not guarantees, agreements. By the time you use an app, you're already living inside those compromises. You just don't see them. The system absorbs the error, masks it, smooths it out until it can't. And that's when wrong code stops being quietly helpful in you and starts becoming a problem. Here's where the story stops being abstract and starts getting uncomfortable. Because wrong code doesn't fail randomly. It fails selectively. Most of the time, it behaves. It stays inside its little box of acceptable error. Engineers test it, simulate edge cases, add guardrails. Everything looks fine until the world changes slightly. A faster processor, a new compiler optimization, a system under load it was never designed for. Take financial systems. For decades, banks used floating point math to handle money. Engineers knew it wasn't exact. Everyone knew. But the errors were tiny. Fractions of a cent. Rounding noise. Invisible. Then someone noticed that if you repeat those transactions millions of times, the noise doesn't cancel out. It accumulates. Quietly, reliably. Some systems didn't fix the math. They fixed the symptoms. Daily reconciliation jobs, error correction passes, adjustment accounts. The code stayed wrong. The results stayed acceptable. Or consider physics engines in video games and simulations. The equations governing motion are approximations. They cut corners to stay fast. That's why characters sometimes vibrate against walls or objects clip through floors. Developers don't eliminate the bug. They tune it, they dampen it, they add invisible forces to hide the instability. The illusion holds until you push the system too far. Now zoom out to machine learning. Modern AI models are trained on noisy data, optimized with imperfect math, and evaluated using metrics that don't fully capture reality. Engineers know this. Everyone knows this. The model is wrong in thousands of tiny ways, but if it predicts correctly often enough, we call it working. This is where irony creeps in. As software becomes more complex, correctness becomes harder to define. What does it even mean for a recommendation algorithm to be right? For a risk model to be accurate? For an autonomous system to behave properly? So teams shift the goalposts. Accuracy becomes performance. Truth becomes probability. Bugs become edge cases. And the system moves forward, powered by code that no one fully trusts but everyone depends on. The conflict isn't technical. It's philosophical. We built machines that are too complex to be fully correct, then handed them decisions that matter. Money, movement, medical outcomes, information. Wrong code doesn't announce itself. It blends in. It works until the day the assumptions change. And that's when engineers realize they weren't building logic. They were building negotiated reality. Here's the turning point most people miss. Wrong code doesn't become dangerous when it makes mistakes. It becomes dangerous when we stop knowing why it works. There's a famous moment every long-running system reaches. Engineers call it the haunted phase. That's when no one dares touch certain parts of the codebase. Not because it's elegant, but because it's holding everything together through mechanisms no one fully understands anymore. Comments say things like, "Do not remove," "legacy fix," "temporary workaround," from 2007. At this stage, the system isn't just wrong, it's fragile. And now add scale. Cloud infrastructure routes traffic using heuristics that assume average behavior. Financial markets execute trades in microseconds based on models that assume historical patterns will repeat. Safety systems rely on thresholds chosen because they worked last time. Then something unprecedented happens. A market moves too fast. A sensor drifts out of calibration. A model encounters data it was never trained to see. The math hasn't changed. The code hasn't changed. Reality has. This is where wrong but working code snaps. Not loudly, not dramatically, quietly. Cascading failures, small errors lining up like dominoes. One service times out, another retries aggressively. A third assumes the first two are lying. Suddenly, the system is technically doing exactly what it was programmed to do. And that's the problem. The climax isn't a single bug. It's the realization that correctness was replaced with optimism, that assumptions became dependencies, that error margins became blind spots. This is why postmortems read the way they do. No villains, no obvious mistakes. Just phrases like unexpected interaction and emergent behavior. Wrong code worked because the world stayed inside its expectations. When the world stepped outside, the illusion collapsed. And here's the quiet irony. The better we get at hiding error, the harder it becomes to detect danger. Modern systems are smooth, polished, resilient on the surface until they aren't. At the climax of this story, engineers don't ask, "How did this break?" They ask something scarier. Why did this ever work at all? So here's the part that usually gets left out of the conversation. Wrong code isn't a flaw in the system. It is the system. Modern software doesn't run on correctness. It runs on margins, on assumptions that the future will look enough like the past, on the belief that small errors will stay small. Most of the time they do. That's why planes land safely. Why your payments clear. Why your phone feels impossibly smooth. But underneath that smoothness is a bargain we rarely acknowledge. We accept code that is good enough because the alternative is code that is slower, more brittle, harder to ship, harder to change. Perfect logic doesn't survive contact with real hardware, real users, real markets. So we build systems that can be wrong as long as they're wrong in predictable ways. The risk isn't that software has bugs. The risk is that we forget where the assumptions are. We forget which errors are tolerated and which ones are catastrophic. We forget that a working system is not the same thing as a correct one. And as AI, automation, and algorithmic decision-making spread into more parts of life, that distinction starts to matter a lot more. Because now, wrong code doesn't just miscalculate. It recommends. It denies. It decides. The future won't be broken by one massive bug. It will be shaped by millions of tiny compromises that made sense at the time. That's the uncomfortable truth. The question isn't whether the code is wrong, it's whether we still understand how it's wrong, and whether we'll notice when the world stops forgiving it. If code can be wrong and still work perfectly today, what happens tomorrow? When perfectly isn't enough anymore. That's not a problem for engineers alone. That's a problem for everyone who lives inside the systems. Done watching. If you like this video, hit subscribe for more cool stuff.